Matter classification, note page 31. So last class we looked at the universe as a whole, and that the universe can be classified into two major areas. Things within the universe that function as matter, and everything else is energy. So something is considered matter if it contributes mass and it occupies space, or we could use the word volume. Matter can be subclassified into two major categories. Materials that we refer to as a substance versus materials that are referred to as mixtures. So a substance refers to the idea of something being pure. If a material is a true substance, it's made up of one type of particle, meaning that all of the particles within that sample are identical to each other. So only one type of particle, all the particles are identical. And because there's only one type of particle, when we look at the composition of the sample, taking a look at the type of atoms present, and we also look at the structure of the sample, meaning that we're referring to the bond pattern, how the different atoms are linked together. And in a substance, since all the particles are identical, they will have exactly the same composition and structure. So everything is completely the same through the whole sample and between samples. So in order to identify, when we look at a chemical formula, whether that matter is referred to as a substance or mixture, we tend to use phases. So anything that is identified as being a solid, liquid, or gas in the realms of our chemistry class will be considered pure substances. Now, pure substances can be further subclassified into two categories which you should be pretty familiar with. So if it's an individual element, it's a substance. If it's an individual compound, it's also a substance. Small differences between the element and compound. So it's considered an element if the sample has only one type of atom. So all atoms in the sample are identical. So all atoms are identical. Versus a compound, okay, that means that the sample contains only one type of molecule. And so that means that we have different types of atoms bonded, and they bond in a fixed ratio. So I'm going to write here, short form, different types of atoms bond in a fixed ratio. So here we go. Let's list some examples of elements. And you already know a few or several different elements. So if we are talking about the element zinc, its chemical formula is Zn. Now if we talk about the element oxygen, we don't use its periodic symbol O, but its chemical formula is O2. But notice that even though there are two atoms, they're of the same type. Sulfur, its most common allotrope, actually has a subscript of 8. But all 8 atoms are the exact same type, so this would represent an element. So when you see only one elemental symbol, right now we're going to ignore any little numbers, those subscripts. If there's only one element symbol present in the formula, then it's a pure element. Example of compounds, and there's quite a few of these that you already know. So our favorite compound, H2O, water. It's made up of two different types of elements, hydrogen and oxygen, and it's always two hydrogens to one oxygen. Carbon dioxide, CO2, at least two different elements, and its formula is always one carbon to two oxygens. Sodium chloride or table salt, NaCl, it's a 1-to-1 ratio. And then that big one from respiration, C6H12O6, that you guys know as glucose, and you know it's always 6 carbons with 12 hydrogens and 6 oxygens. Just a few examples. Now let's take a look at mixtures. So if a substance is considered pure, mixtures are not pure. Okay? So mixtures are made up of, I'm going to use the word multiple, so multiple types of particles. The particles in the sample are different, or I should put not identical, might be a better word to put here, so I'm going to write here not identical to each other, because they have, and probably the word different would fit better here, different structures. So because there is more than one type or multiple types of particles, they are not identical, they have different structures. That means that the composition can vary within the same sample or between samples. Our most common phase for a mixture is called aqueous, A-Q-U-E-O-U-S, or its abbreviation is AQ. And mixtures, they can be separated by a physical process. So there are already some great examples of separation techniques that you're already familiar with. Now mixtures, they can be further subclassified with these two fancy words, homogeneous versus heterogeneous. And what this looks like, or what this differentiates between, is the distribution of those particles. So I'm just going to write the word, the distribution, or the blending of the particles. So you should recognize these two prefixes. So HOMO entails the idea of same, where HETRO represents the idea of different. So if it's a homogeneous mixture, that means it has the same distribution or blending. So we're going to say a uniform blending of the particles. So when you look at a homogeneous mixture, a lot of times the most common ones look like a liquid. Okay, so I'm going to put a little star here. Looks like a liquid, because the most common homogeneous mixtures that we come across is something blended with water. So looks like a liquid. So here's a very important word. Anything that we describe as a solution is our best example or buzzword for a homogeneous mixture. So some great examples here of homogeneous mixtures would be like coffee. Can't live without coffee in the morning. So coffee, Kool-Aid, tea would be another great one just off the top of my head. Versus something that is heterogeneous, that means that it lacks a uniform distribution or blending. So when you look at this mixture, you can see some visual differences. So here, instead of having a uniform blending of particles, okay, how should we word this? So instead of having a uniform blending of particles, we can see layers in the sample. So we see layers. We see particle separation, meaning some particles might settle to the bottom, so we see layers within there. And, you know, it looks visually different throughout the sample. Okay, so if it's heterogeneous, there's some sort of laying, particle separation, and you can visually notice some major differences here. So some great, oh, and I'm going to say this, that if it's a heterogeneous mixtures, big clue at home is that if you have to shake or stir before use. So if it's a material that you're going to use and it says shake or stir before you use it, it's definitely more heterogeneous in nature. So a couple of great examples of heterogeneous materials. My personal favorite one is pizza. You know, you can see those layers. Many salad dressings, especially like that Italian dressing. You got to shake it before you dump it out. And I'm going to say like muddy water is another great example. So you know that you probably don't want to swim in that pool or go play in that mud puddle because you see those big chunks or those extra big particles that make the water look a little bit dirty.